So, Ella, last day we looked at magnetic field. We looked at Lenz's law. This is a really neat application of Lenz's law. This is a ring falling in a magnetic field. I think it's a ring falling in a magnetic field from MIT. So you might remember the demonstration we did with the copper pipe and the magnets falling down the copper pipe. So this is also a very similar phenomenon. So we have an aluminum ring with a slice removed, so it's not a continuous coil. We have a complete aluminum ring. And then we have an aluminum disc. You can think of an aluminum disc as a whole bunch of rings all glued together as they get bigger and bigger and bigger. You can think of it as a whole bunch of rings. Then we have a pretty strong electromagnet. So right now, with no magnetic field, nothing. No magnetic field. Ooh, no, sorry, it was turned on. What did you notice? Didn't fall as fast. That was Lenz's law. This one here, because it's a series of rings, way slower. By the way, that's a really strong electromagnet because look at those solenoids. That's got to be probably 10,000 turns of wire in your solenoid. B equals mu naught N times I over L. N is really big there. And they're probably running a fair bit of current through there too. All right. Oh, we're going to get a close-up. So here's the disc with a gap in it. Lenz's law. And you can see it goes into free fall for a split second in the middle because there's no longer a changing flux. And then it kicks in again. And then this should be the disc. Or is it, this is the one with a gap in it. Okay, this is the one with the gap in it. We shouldn't notice any effect at all. Straight through. Okay. So, and then the disc. Much more noticeable. Lenz's law. All right, let's get to today's lesson. Recall how an electric motor works. We have an armature and it spins. Okay. Once the motor starts, so first of all, Aryan, we have this. We send current in this direction. So let's look at this left arm. This left arm, current is moving into the page, if you want to think about it that way. What direction is the magnetic field pointing? To the right. So if all of you point your thumbs into the page, fingers to the right, this section will feel a force downwards and it'll start to spin. In fact, let's call that FB. It'll start to spin. Is that all right? I think I did that right. What happens, Ashley, though, as soon as it starts to spin? As soon as it starts to spin, now we have that proton sitting right there also moving downwards because it just started to spin. Not only is it moving into the page, it's moving down the page. So point your right thumbs down the page. Magnetic field still to the right. What direction will the proton feel a force? So I'll stand up so you can see. Now it's moving down the page, magnetic field to the right. Dean, it's going to feel a force out of the page opposing the current that's coming in the page. You're going to get what we call a back voltage. You're going to get current going against the source current. Okay? So if we're writing our notes here, the charges will experience, come back, uh, magnetic force pushing them against the source current. And because charges are moving, we have charges are being separated. We have a voltage. We call this back voltage or back EMF. As soon as a motor starts to spin, it starts to create its own current and voltage going in the opposite direction of whatever's causing it to spin in the first place. And by the way, that's a consequence of Lenz's law. We should elaborate on the concept of back EMF. So the charges will experience a magnetic force pushing them against the source current. Whichever way, Kyle, you set up your motor, whichever way you spin it, you can play around with it. As soon as it starts to spin, you're going to say, ooh, now the charges are moving perpendicular. Ooh, now they're moving backwards against the direction that we were sending it in the first place. Let's elaborate on this. It says, fill in the key facts about back EMF. The back EMF is created by the spinning armature. It's created by the fact that the protons inside the armature have suddenly started moving. The amount of back EMF, it's proportional to how fast the motor spins. The faster it spins, the bigger the current you're going to be getting back in the opposite direction, the bigger the back EMF you're going to be getting in the opposite direction, because you'll have more charges moving per second. When the motor starts out at rest, well, before we start the motor spinning, what's the back voltage as a number exactly if it hasn't started spinning yet? Every electric motor has a maximum operating speed. Fahim, the maximum operating speed is when the back EMF equals when it's speeding so fast. So let's suppose you've hooked it up to a 12-volt battery. When the motor itself is generating 12 volts, but in the opposite direction, because if you have a 12-volt gain and a 12-volt loss, what's your net voltage overall? And so that's the equilibrium point. That's maximum speed. There's no longer any unbalanced force causing it to speed up. Okay? If we write an equation, it really looks like this. So I'm going to use some notation. I'm going to use that for the supply voltage. And I'm going to use for the back EMF. Okay? And here's what it looks like. If you want to calculate the back voltage or the back EMF, first of all, that's at maximum speed. Okay? What if you're not at maximum speed? Well, then it's minus I times R, and you can point an arrow here. This is the voltage still left in the armature. The voltage that's still left in the spinning arm. Oh, and fine, let's be obvious. Hannah, what does I stand for? And in this case, it's the current in the armature. In the armature. And R is the resistance of the armature. And we're using a lowercase r because ideally, Hannah, you don't want your armature to have a lot of resistance. Otherwise, you're just heating it up like a stove, which wastes a lot of the energy. So a lowercase r is meant to show small resistance. Did I give you this on your formula sheet? I did. Okay. Couldn't remember if I had. So if we turn the page, the mathematical analysis of this is pretty straightforward. The equivalent circuit for a motor, so here's our motor, there's our supply, there's the brush contacts, here's the actual armature. It's the same as having a supply voltage, and as it starts to spin, we have a back voltage with a battery pointing over here. In other words, here's your supply voltage, and when it's not turning at all, that's which way the current is flowing. The faster it spins, the more current you get flowing in the opposite direction. What's the maximum speed? When the two currents cancel each other out. Exactly. How do I figure that out? I times R, because our I equals V over R. All right. So you can, of course, really what we're saying is this. The source voltage is going to be that plus that, gravity. But the back voltage is your source voltage minus what you're losing in the armature. So all I did was I plus the IR over to get the source voltage by itself. Let's apply some of this. Oh, I have a formula. Wow, I put it here? Okay. So V back equals the EMF takeaway I times R, where the EMF, that's the supply voltage, that's the back voltage, and the back voltage equals 0 when it's at rest. Maximum at maximum speed. Ideally, it exactly cancels out the source voltage. That's your maximum speed in our perfect world. We're ignoring all the other stuff that can go wonky. Varies directly as the speed of the motor. I is the current through the motor. R is the resistance of the armature. Let's do a question with numbers. A motor is connected to a 100-volt supply. You know what? That's your EMF. Initially, with the motor at rest, the current is 5 amps. Underline the word at rest. That's going to be kind of an important word. When the motor is running, the back EMF is measured at 20 volts. Find, okay, A, the resistance of the armature. Victor, are we talking about back EMF?
Sure, yes.
So we have this equation here. It says V back equals EMF minus I times R. When you're at rest, what's your back voltage before it starts out? So I can actually modify this, and I can go 0 equals the EMF minus I times R. Almost always, Ella, they'll give you the current when it's at rest for this reason, because how would I get, it wants me to find the resistance, how would I get the little R by itself? I think, Ella, what I would do is I would, first of all, plus this there, get rid of the negative, right? We'll have I times R equals the EMF. Get the R by itself. Yeah, in fact, this is Ohm's law. I'm writing it like this, but Ohm's law, R equals V over I. I'm using the EMF symbol because I also know I have a V for V back, and I don't want to get them mixed up. So I'll typically use the EMF symbol for the source and V back for the back voltage. What's the source voltage that we're plugged into? Yep. When it's at rest, what's the current running through the armature? No. So what must the resistance of this armature be? You might even be able to do it in your head. 20 ohms, yes? I won't always walk you through part A. I might just jump straight to part B. But to do part B, you do need the resistance of the armature when it's at rest. Dean, what's part B you want me to find? Okay, so let's bring in our back EMF equation. What does it want me to find?
Okay.
Get the eye by itself. What's right in front of the eye that I don't like? Swappy dance. I'm going to plus that there. I'm going to minus that there, if you don't mind. And I'll get I times R equals the source minus the back. Well, get the I by itself. Yeah, and the resistance isn't going to change. That's a physical component of the armature, but that's why we had to find it first, and that's why they gave us the current when it was at rest, so that I could find the resistance. And now I can walk over here. Dean, what's the source voltage? What's the back voltage at speed according to this question? How many amps are running through this motor? I think it's 4, but double check me. Yeah. So this, believe it or not, Fahim, it's terribly profound. Don't turn the page yet, Ella. As we speed the motor up, what happens to the back EMF? Does it get bigger or smaller? Bigger. What happens then to this answer? If we're subtracting a bigger number, the source isn't changing. Eric, what happens to the current as we speed the motor up? What? No, you were right. Gets smaller. This is why electric motors are so efficient. The faster you spin them, the less current they use. For cars, the faster you rev them, the less gas they use? No. Not only that, current is what causes circuits to heat up. The faster you spin the motor, the cooler it will run, the more efficient it is. For cars, when you rev them up, do they run cooler or are they less efficient for gas cars? This is why electric motors are so nice. Example 4, I like example 4, I like example 4. Example 4 is a nice question. The resistance of the armature of a motor is 12 ohms. At operating speed, when connected to a 120 volt outlet, the motor draws 6 amps of current. Find the back EMF. Oh, this is straight plug and chug, I think, because I think I can go like this. I think I like example 3 better than example 4. That's a much more interesting question, but okay. V back is going to be... Ashley, did they give me the source voltage? Yeah. Did they give me the current in the armature at this point in time? And then notice they said at operating speed, so this is not when it's at rest, this is at whatever speed we're running. Did they give me the resistance? You know what? It's going to be 120 minus 6 times 12. 6 times 12 is 72. It's going to be 120 take away 72. It's going to be 48, I think. Double check. As we spin faster, Eric, what happens to the current? So what happens to the subtraction number here? Gets smaller. The max you can get is when the back voltage equals the source voltage, because then they cancel each other out. When an electric drill is prevented from turning, the motor heats up. How can we cool the motor off? Get it to spin as fast as it can with no load, because the faster it spins, the smaller the current in the armature, because it's canceling out the source current, and current is what causes wires to heat up, because current is the number of charges per second. If you're ever using an electric tool and you can feel the tool is heating up, it's going to be heating up because it's turning slowly, not at full speed, under load. Lift it up, hold the trigger down, keep your hand on it, and you'll feel it cool off very rapidly. Again, electric motors, they're at the most efficient, they're at their coolest running, Kenta, when they're running at their maximum. Is that the same for gasoline motors? No! Last one. The back EMF of a motor is 4.2 volts when operated from a 6-volt source. When held stationary, the current in the motor's armature is 5 amps. Okay, Arian, what does A want me to find? Of the armature. To do that, Arian, you're always going to use when it's stationary, because when it's stationary, you know the back EMF exactly is a number. What's the back voltage exactly is a number when it's not turning? Okay, so we're going to start out with V back equals this. Except when it's stationary, Arian, what's the back EMF? 0. Get the R by itself. I think what I would do, Arian, is kind of a swappy. I would plus the IR over, yes? And in fact, you're getting just a version of Ohm's law, R equals V over I, source voltage over current at rest. Arian, what's the source voltage? Thank you. What's the current when it's at rest? Good. What's the resistance of this armature? Units, resistance, ohms, right? Good. Jaya, what's B want me to find? Okay, we'll go V back equals E minus IR. We'll get the I by itself. I'll swappy dance, I think, first. Yes? And I'll get IR equals the EMF minus V back. How would I get the I by itself, Jaya? Okay. Folks, probably on the test, I won't ask you part A first. I'll just say, tell me the current at its normal operating speed. Or I'll give you the current at its normal operating speed and ask you to find the back EMF. But first, at rest, I will give you the current at rest. You'll need to realize I can use that to find the resistance of the armature. So it's going to be 6 minus, what was the back voltage? 4.2 divided by 1.2. What'd you get? Units. So I have some videos and some neat applications, but first let me say which questions you can try. You can try number 1. Try number 2. You can skip 3. You can skip 4. 5 is good. 6 is good. 8 is good. Let me hit pause.